Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk, we got some fan mail.
Hot dang.
Yeah, and a suggested topic, which I thought that would be perfect for us to talk about.
Oh, right. Let's dive into it. What you got, Fred?
So it was in email, or no, it was through LinkedIn, which is fine either way.
Yeah.
And it said, "Hi, Fred, really appreciate your podcast. I'm a big fan!" Exclamation point. Like, cool, made my day. Appreciate it when that happens. And one possible topic you might consider is how traditional reliability approaches no longer work for newer, more complex products. For example, older PCBs, printed circuit boards, had 4 to 8 layers, but AI PCBs today can have up to 80 layers, introducing entirely new failure modes that traditional reliability methods don't fully address. Just a thought, wishing you a wonderful afternoon. Cheers. And when we've had multi-layer, 850 and higher circuit boards for a long, long time. I worked on those 30 years ago.
Right.
But they were in very, like AI boards, these very high speed, high performance type stuff. And it's in the news more now.
Right.
The technology and the frequencies of electronics, the
changing
new materials,
yes.
The new materials that we're dealing
with. The dimensions are changing. The spacing is changing.
Well, just think of how many more electronic boxes we've shot up into space in the last 10 years versus the last forever,
right?
And stuff like that.
Right.
And so it was, I think in general,
right.
You would totally agree that traditional reliability approaches don't work well for very complex systems. And by traditional, I'm thinking one of both of us is our favorite traditional approach is the parts count prediction.
Well, parts count, you keep calling it parts count, but there's a lot more to the Military Handbook 217 philosophies way back then, mostly based on Arrhenius and fit rates. And the fact that fit rates are
grand averages of what they could find.
And for every 10 degrees C, you double the fit rate, which is not true at all for any device or component. But
it also
most engineers know that.
Yeah, and it didn't account for wear in or wear out, or it didn't account for anything other than constant failure rate.
Right, but that was the basic, and just like Christianity started with Catholicism, reliability engineering started with predictions through the electronic, tables.
No. You know better than that. There was also the physics of failure stuff. There were plenty of engineering papers and studies out about failure mechanisms and how they manifest. And here's a distribution of how they go. And here's the deterministic formula for how this creeps or whatever.
For those.
But the issue is that it was very expensive to do those kinds of analysis on your whole system because the computing power wasn't there. And so we simplified it on big, complex things.
Well, I would say also there was no comparison with the calculated and modeled reliability and then the actual field reliability.
Oh, no.
There was no correlation whatsoever with it.
And everybody kind of ignored that.
No, right, because nobody goes back and looks at what the,
Well, that's not true. There are people that do.
Well, okay, there are people that do, but they come to the, management and you say, this is what we calculated. Because we know, you and I know, that there's so many other factors that go on the time period from early prototypes to production, and during production, a component procurement engineer, procurement guy, and the buyers change a component, don't tell the engineers or don't think it's any different. There's just all kinds of things. It might be a new use environment. It might be a new application the customers come about with. There's just a bizarre number or not bizarre, but a huge number of of factors that can go into the variation of the quality of the manufacturing. And that's why, my philosophy of building the most robust design early in the design stage helps the product be able to tolerate more variation in the components and usually the use environment too. So,
well, here's the
but
rub
I've
here
been
for
okay.
here's the rub we got here, Kirk. Is
Okay.
that,
Okay.
using as examples, like a computer's, like a home computer circuit board, early ones probably only had 4 to 8 layers. And now they're so dense and so small, and they're even embedding components within the circuit board,
Right. Right.
printing them right inside
Right.
it.
Exactly.
What would you change in Hull to identify the weak links when it does that kind of change? You go from, say, 8 layers to 20 layers, and you have embedded components. What would you change in the Hull?
Well, I guess I wrote about it, and there's a paper I have on my website, and and I'll probably put it in some other places. I hope recently, and I put it up. I think I put it in yours, but one of them is the fact that timing. You can skew the timings of, and used it used to be, because of the frequencies that we're using now are incredibly higher than the 80s, 90s,
Yeah, we were
2000.
in 500 megahertz
Right.
in the
So
old days.
things that were second or third order phenomena are now becoming first order problems with the spacing of the layers, with the
the changes in the dielectric properties of temperatures,
the crosstalk, expansion, contraction. And I've always wondered why engineers didn't focus on some of the timing and signal integrity issues that show up in mass production. Or and I've there was a Allied Teleson that did use thermal stress and extreme thermal stress to skew the timings, and that's what it does. I mean, we know that when something gets a component gets cold, it has actually can operate at a higher speed. And I show this in a graph for 1 octo buffer in the paper, that timing thermal stress changes the electron mobility, and you can skew the timing by thermal stress. So, and also, the what we talked about earlier, the thermal coefficient expansion, the expansion of all those layers. And you talk about metal and FR4, if they're still using FR4 as a substrate for all the layers, they probably have developed better.
There's better ones that have better dielectric properties.
Right, that have good dielectric properties, but still you have the problem of crosstalk, signal integrity, speed, possible what do you call it? Race conditions, those kind of things that you can find through. You have a potential of using thermal stress as a tool, and that's what I talk about. It thermal stress, a tool for software signal integrity, uh, and as these electronic circuit boards and assemblies become more dense and more concentrated and higher speed, it's imperative that the variation in the manufacturing is going to be a bigger issue, and consistency of all the spacings and the trace lengths.
Hopefully, no adhesives.
Well, I don't know how they put the layers together, Fred. I really,
I've seen that done. I've seen that done. It's it's getting to where the high end boards are getting to be like putting together a circuit or a CMOS chip. They're doing lithography almost.
Right, they're doing probably chemical vapor deposition or I don't know.
It's amazing how there's a handful of techniques, and it gets
or laying down metal. Yeah,
it gets really into the chemist world, and how this stuff all works. But it's also, how do you get the dimensions and separations clean. You can't have terrible, if everything's just a few, a couple millimeters apart and half a millimeter makes a huge difference. It's not the old deal. I made a circuit board once in college. We had a copper coated plastic and we etched it. They don't do that anymore. They don't do that. It's way sophisticated. Now, one of the issues though is varying timing and doing all that stuff. You have to be able to measure it. What's the effect on your system? And if your circuit board has 800,000 primary functions, just doing a test loop and saying if everything's there or not isn't sufficient. You got to have all kinds of really interesting equipment to monitor the functionality of your board. That becomes a big barrier to really understanding how robust your product is.
Right, and I would also say that one of the things I noticed that one of the manufacturers or common was to do one test on one section of the board, then do a test on another section of the board. They individually test the different functions of the board, but never or rarely running them all together as hard as you can in a stress environment. That was rarely done. This works.
Yeah.
But I'm thinking, well, you're not really having the system interoperate, to all the subsystems and all the functions. And it takes a lot of time to test everything. I mean,
well, it takes a lot of time to design the test rigs. And I often worked with the test engineers, the folks that were primarily in production facilities saying, all right, is this board is it working now or not? And because they had stepped through all of the different nets of circuitry on the board and which one did what and what, should this capacitor be this value or this value, or what's the voltage on this trace and stuff like that. But then they were also getting into running simulated loads to see what the functionality was and timing and things like that.
Well, I know the simulation software has gotten a lot better.
It's got better, but it's
Spice days that I learned
it
in
was
college.
pretty basic. But the idea is that there's people in the organization that are already working closely with the design team, so they can say, all right, this product is working or not working and meet its requirements. Well, I'm interested, does it work under stress? And so it's kind of hijack one of their test rigs in their knowledge and get them over there next to my lab where I'm stressing it. And every now and then they were like, no, we're too busy. We want to talk to you. We're going to make it right. You just don't worry about it. It'll be perfect when we get done. And I always then kind of shut them up when I say, does it work outside? Does it work after 10 years? Does it work?
Exactly.
Kind of thing. And that usually said, oh, okay. Let's roll it over there for a day and see what we can get.
Yeah. Why wouldn't it? They said to Fred. And it's like, well, let me show you the
list
factors.
The ways.
Let me list the ways it can fail. And all this is no good if your manufacturing is not consistent. At any time, any good product can be a bad product by a excursion, as we used to so politely put it.
Somebody messed up.
Somebody really screwed up. And I guarantee you won't find that out a year from then. Because that's buried. And this is why traditional reliability engineering hasn't ever really changed to me very significantly in the last 3 decades. Since I've been teaching this stuff. It's just, and I never came from the standpoint of CRE or anything like that. I came through working in the field, service, repairing implanters, working on semiconductor manufacturing equipment, seeing what actually failed and putting it together.
Yeah.
And
now you and I do agree though, and you mentioned it earlier, is that, any product, any design, it's not just reliability, and we're working with all the other trade-offs. Now, one of the things that I think has been missing from CRE and traditional approaches, because I've run into, and Carl and I have talked about it a couple times, you go in and see we've got a reliability engineer. What do they do? Well, they just fill out paperwork. Nobody reads it. Kind of thing. Like, that's not reliability engineering. So Carl and I wrote the book on, you got to focus on what are the decisions? What is it you need to know? And why is it important, and tie it to your business model kind of stuff. But the idea is that you don't, there's a very strong message in the book is don't do what you did last time. You have a different product, you have a different circumstance, you have a different level of knowledge about what works and where the risks are and all that stuff.
Right.
If when I hear traditional reliability methods is, oh, we're going to do an FMEA and then we're going to do a halt and then we'll do some accelerated testing and we'll call it a day. And I'm like, no, those all may have been perfectly useful for project 4 times ago. And then you had a great success out of it. And now management says, well, just do that. We don't have to think about it anymore. Just do that and we'll be all right. And Kirk, you get a great success out of the introduction of HALT, and then they say, we'll do it on everything all the time. And then we both know that's a colossal waste of effort. It has to be matched to what you need to know and what's the purpose of doing that activity or test or method or whatever. And so, like you don't start with the methods. Just because you have a thermal cycling lab doesn't mean you have to use it. Is that the best method to find out if you have a problem with that stress being applied?
Okay. If I want to find out how something is going to fail in time, over time, because of fatigue damage and usage and chemical reactions, the thing that is universal with no matter what the dimensions, what the speed of electronics is that environmental stresses and voltage variations and different uses in different environments. That's always going to be probably true that those stresses are going to increase the fatigue damage and shift the functionality, as I mentioned, with the cold and hot, changes the timing. And as you get tighter and tighter parameters for that timing, down to nanoseconds, that the trace length of something on the circuit board really makes a difference on how far that signal has to travel. You're talking still about the fact that over time, the materials will change, the bonds will change, the material interfaces will change, and the characteristics, maybe the chemical characteristics, the spacings, and all that will change. The boards and the signal integrity and a lot of the joints and bonds will break down over time, no matter what dimensions you're talking about. So that's why I'm very happy my book is still selling after 7 years or 9 years.
It's been a while.
That I believe it's going to be universal. That if my philosophy is as technology changes, the limits of fundamental limits of technology may change. And
the approach is fine. And no, I totally agree, Kirk. But what you're stressing though is not just go do HALT, run the standard profile.
No.
You're saying thinking about it. Think through
about it.
What are the stresses? What's important? What do you need to find? What are you looking for? That is not traditional reliability in my mind. That's been missing with so many of our standards, so many of our activities. There's a MIL standard. I think I've done every test in the book. It was
810?
810, except for ballistic shock. There's the one thing I haven't done.
The great thing about 810 is that there's no definition of what constitutes a failure. That's up to you.
Yeah. And we always test for success. We're success-oriented way too often.
That's great.
The issue is that we have lots of techniques, lots of methods out there, lots of ways to apply stresses alone or in combination, lots of ways to analyze data, failure analysis, modeling, all kinds of cool stuff out there. Don't start there. Start with what do you need to know? What questions do we need to answer? Will this work? Will this work for 10 years? Will this work for 50 years?
What has worked in the past? What hasn't worked in the past? And do we have any of those elements in the design or product?
And by work, you mean the product itself, not the test methods.
The product. What the field.
I'm
saying, yes, go look at your field warranty and also, longer term than that. And hopefully you'll have some that have been years in the field and you can have an idea of what the degradation has been on the product over time and what the risks are. But
Hmm.
it's all, to me, it's not just, you're not isolated. It's suddenly a company pops up and makes a brand new product's never been made before. Most of the time we have a history. Also, we have an understanding of material science and material interfaces. And just, as we talked about with a good reliability engineer, you have a lot of different knowledge bases. But the one thing I want to say is, the one thing that doesn't change is material and assembly fatigue over time and stresses. And that's going to always happen with every component, every design in the future. They're going to be more used in more uh, difficult applications, probably, or more stressful applications in the future, as they get to
Hmm.
be more small and compact, and can be part of a lot of different things that haven't been thought of before, now that they've gotten down to smaller and smaller packaging. I
Oh,
mean, we couldn't imagine a color camera in every car, a backup camera. I mean, now look at
that's
that.
standard, pretty
It's a
much.
standard. You got a big LCD screen and touch screens in the car.
Yeah. Well, think of it this way: is that I saw an article a couple weeks ago that was we're kind of running out of futuristic inventions that Star Trek did in the 60s,
Yeah,
except for the
right.
transporter. The transporter we're still
Yeah.
working on,
And you be the first one in it, I'll tell you.
warp drive and transporters. We're still working on those.
Yeah, yeah,
But like
exactly.
tablets, they used to use,
Absolutely.
they had
Yeah.
tablets, they had communicators,
Right. Right.
all kinds of weird stuff like that, and doors that had a motion sensor open and close. If the camera was in the right angle, you could
And
see
we
the
will
guy's
have,
hand pushing it back and forth.
yeah, right. Right. But now it's just common. We go up to a door and we expect it to slide open.
That's right. Even if it's a solid window, we keep walking.
Of course, I thought I was fascinated as a kid in the 60s, where I could step on a pad from at the grocery
Oh
store
yeah.
and the door would open, but
Hmm.
now you don't even see it. It's ultrasonic.
Well, I ran
Uh,
into one of those. I was in junior high, and my buddies and I were on our bicycles, and we'd come up
yeah,
to an intersection, and it wouldn't sense us there. It was a pressure plate. So we'd
right.
get off our bikes and jump up and down until the light would change.
Right. Yeah, it's getting more sophisticated, but it's still the fact that the world is stressful, the outside world and people's use and
Expectations, that changes
expectations of
too.
right. In fact, we now expect our iPhones not to shatter when we drop them necessarily, or be if they dropped in the toilet or in the bathtub or in the pool,
Hmm.
that there's a very good chance that they'll still be okay when we pull them out.
That's right. Just pull it out. Don't let it sit there for 6 hours and put electrodes across it. That would be bad.
Yeah, and what did my daughter do? And I said, yeah, go ahead and put it in rice.
Yeah.
And it
Suck out some
worked.
moisture.
She
Yeah.
said, "Thanks, Dad," and so it did. But yeah, so they've and it'll continue to evolve. I just think we don't know what's coming next. We don't know what the new breakthrough will be in electronic miniaturization, but we know that environmental stresses, voltages, and those things will always be a factor in aging the electronics and causing material changes, chemical changes that may cause a failure in the future.
Yeah, and the last line on Mike's message is new failure modes that traditional methods don't fully address. Well, we're not limited by only using what's in the toolbox. Those halt came about because somebody thought, well, this is a good way to do it, and it wasn't done before. So
Okay, but
let's think through, what do I need to know? How can I do it? And it might not be out of 810. You're going to have to create your own way to go do it and apply these stresses. And somebody
right,
told
but
me that it's really difficult to do humidity and vibration because the humidity goes after the vibration elements and corrodes them. Like, okay, the world
yeah,
does it just successfully all the time,
right,
you know.
right.
So you got to think through it and consider, what do you need to know and what do you need to apply. And
Fred, I've always said that Halt is very adaptive, highly adaptive
yeah,
to the product. Okay,
yeah.
so I've addressed this before, that you've got to think about what it is that you're trying to do. If you've got polymer tubes, I know they're going to get stiff and hard and not going to be
Mm-hmm.
closable with whatever mechanical thing plunger that you might shut them off with. But the electronics at that temperature are not going to have any problems at all. They're just,
they'll be fine.
fine. So you've got to think about how you could separate this and what's what's relevant for the product as far as giving it real stresses and getting to the boundaries of what its capabilities are. And so I just, that's again, comparative boundary analysis. There's just a lot of things that you would use in HALT. And one thing that Greg Hobbs didn't really address, and that was the skewing of timings that you could get, because at that time, electronics back in Greg's day weren't that high speed, but now they're getting up to just nanosecond, and gigahertz, what terahertz. Well, I don't know what the speeds are clocks now, but it's the bus speeds.
Multiple giga, right?
Right.
But what it's really to the heart of Mike's comment and for the idea is that, as the technology evolves and changes, that, skewing and temperature effects on timing, things like that become more and more relevant. And it's not that everything else goes away. We still got to do good solder joints. We still got to do good assembly processes.
Right.
It's getting more difficult in some areas.
Right.
And the fundamentals of what we do is, what's the risk of that failing and ruining our day? Kinds of things, and prioritizing and finding issues and solving them.
Right.
The fundamentals haven't changed. The techniques and methods we use to prove it or discover issues, things like that, that's got to evolve as the technology evolves. And that's part of the fun part is we keep inventing new things and we get to go break them in different unique ways. And so I always enjoy that part.
Well, I think HALT will evolve too, and it has a little bit. I've tried to push it a little bit with my my address on the next generation of HALT and HASS. So I'll put links to the paper on thermal skewing, thermal stress, and signal integrity problems on our notes so they can read it.
Well, I want to shout out to Mike. Thanks so much for the fan mail and that topic suggestion. I knew it'd be fun to talk to Kirk about this one. And then if you've enjoyed the show or don't, let us know. If you've got an idea or a topic, we always are asking for it. If you've got a question that this episode sparked, or if you have another idea of things you'd like us to talk about, head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us there. Kirk and I and the other hosts are available through LinkedIn and our About pages on the site. So plenty of ways for you to get in touch. What did you think? We got fan mail. What a deal, eh?
I hope we can get more, and certainly want the questions that are most relevant to those listeners out there. But we also love to hear your feedback and what you liked and what you don't. Let us know.
Yeah. Thanks so much, Kirk. We'll talk to you soon.
Fred. Take care.
Take care. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.